3.1 lesson. In chemistry, K has a weirdly large number of uses. Of course, it's potassium and it's even Kelvin temperature, but also, and very significantly for this chapter, it is the equilibrium constant. It's the equilibrium constant. So it's a unitless number that shows the relationship between the products and the reactants. In a gas or an aqueous system, things that can flow, things that have concentrations, put a note, not a solid, not a liquid. We're not doing solids and we're not doing liquids. That's not an E, that's a cursive L. Solids and liquids don't have concentrations. And when we say that something is at equilibrium, we mean that it's running equally left and right. That's why we're talking about gases or aqueous solutions. So it has to be able to go right and yet also left. We use the double arrows or sometimes just this, handwritten, more usually like that. And when it's at equilibrium, it's running equally to the right and to the left. We're getting 1 and 1, 1 and 1, 1 and 1, or 1,000 and 1,000, but the rates are equal. That doesn't mean that the numbers of moles on each side are equal. You could have 10 and 1. You could have anything as long as they keep exchanging at the same rate. Then it's at equilibrium. It has nothing to do with the numbers of them that you have in this beaker at this time. You could have 99 of this and 2 of that. It doesn't matter. That's not the point. The equilibrium is the rate, equal rates of exchange. So in that sense, the reaction has sort of stopped, because if you come back in 10 hours, you'll get the same thing. You'll have the same concentrations because they were exchanging equally. You'll have the same number of moles of A and B. So it depends on your viewpoint, but it's kind of like the reaction has stopped. And all gaseous and aqueous solutions that can reverse like this will settle to an equilibrium. I would jot that down too. And K will be true at equilibrium. When equilibrium has been reached, K will be true. What is K? And here's my pet phrase for it myself. I would write this down and memorize it. Boy, does it come up in AP classes. Products over reactants to the power of the number in front. I'm telling you, it comes up about 100 more times. So how do you calculate it? What you do is you take the products to the power of the number in front. The coefficient here becomes the exponent over the reactants, the molarity in this case, because we've got Kc. By the way, Kc is for concentration. Kp is for pressures. There's a few others. We'll leave them for now. If we're going to use molarity brackets, then we're getting Kc. We take the molarity of B and take it to the power of small b. Take the molarity of A and take it to the power of small a. Now this, of course, is just the generic form, but at equilibrium, K will be true. So if K is 5, then this to that power divided by this to that power will be 5. And it will be 5 for this reaction at equilibrium at this temperature. If you change the temperature, that's cheating, and then K changes, which is a discussion for another time. But it will be true. It is like a law of the universe. For this reaction at this temperature, K has been determined. Now we can't make up K. It's a function of the universe. So we just find it. We just determine it. If you're going to get Kp, then you need the pressure. Notice that it's not brackets anymore. And pressure is usually in atmospheres. I have seen it done in torr, which is sort of yet another discussion. But anyway, the pressure to the pressure of B to the power of the coefficient over the pressure of A to the power of the coefficient. Remember, the A there becomes the exponent here. If you really want to get nerdy about how we get there, you can read through this. It's not on the test or anything, so I'm going to leave that to the reader. This is not required on the test anymore either, but you can convert between Kp and Kc because they are conceptually the same thing, but they aren't numerically the same thing. You won't get the same answer for the same reaction, even a gas one, if you do Kp and you do Kc, because the pressure numbers will be different than the concentration numbers. And because you might be squaring things and so forth, they're not necessarily the same thing. So there's a conversion formula here. R is a constant. As I recall, it's 0.0821. And it just makes this be an equation, because without that, then the right side is not equal to the left side. It must be adjusted numerically so that it's actually equal. Also, that's delta N. N is often moles. I know that should seem like it's M, but small m is mass and so forth. So somehow N became moles, as in PV equals nRT, N is moles. This is delta N, it's change in moles. So if you went from, let's say this was 2, you went from 2 moles of this to 1 mole of that in the standard reaction then, didn't you? So the change was -1, so N would be -1. If it was one of these and 3 of those, if B was 3, then and A was 1, you'd be going from 1 to 3. So you went from 1 mole of this to 3 moles of that. So in this case, delta N would be +2 because the moles grew by 2. So I said K is only true at equilibrium, but you can do the K math at any point. And in fact, if you do, it can be really instructive. So we call it Q for quotient. And it's snapshot K is what I call it. It's K for right this absolute like nanosecond. But Q is only true for this moment. Everything will settle down to an equilibrium, I said, which means everything will eventually arrive at a situation where K is true. So if K is 1 and you do the K math on your current situation and you get 2, it's too big. It's going to lower. Now, how quickly, we don't know, but it's going to lower, and that 2 is going to come down to 1 at some point. So here's a really simple example. Here's my dumb stand-in reaction, and we have these molarities. Now, if it's at equilibrium, you'll get Kc, 0.5. But if they're this, then what do you get? Let's do the math on this. Products over reactants to the power of the number in front, and we get 0.33. Well, we did not get 0.5, so the system is not at equilibrium. It's smaller, which means we have not enough numerator for it to be 0.5 and too much denominator for it to be 0.5. Now, all these systems will settle toward reaching equilibrium, and this number is headed for that. How will it do it? This needs to go up, this needs to go down, which means the system needs to make more products, because remember, the products are in the numerator, and burn up some reactants because they're in the denominator. They're going to get lesser here so that the number can grow. That means the system will shift to the right until such a time that this math, using the new values here that will become true, gives us 0.5. So here's a nifty little example. I'm not bragging, I didn't write it. It's very well constructed. Here's our reaction. So a 1.2 atmosphere sample of the reactant was put in an empty container. So it's an empty container, huh? So how much of this was there to begin with? None. Even when we put this in, there was still none of this. After equilibrium was established, the total pressure was 1. And in case you haven't been told this, remember, total gas pressure is the sum of the partial pressures of the individual gases. So here, pressure total will be the pressure of the gas number 1 plus the pressure of gas number 2 at any given point. Well, they said when it's at equilibrium, the sum of them is 1, right? The pressure of this and the pressure of that at equilibrium is 1. Okay, now that gives us something we can build an equation out of. I'll tell you how we get here. Let's build what I call an ice box, and this is pretty standard. Initial change at equilibrium, and we're going to find Kp, which makes a lot of sense because we were given our data in atmospheres. So how much did we have of this? 1.2 atmospheres at the beginning. How much do we have of this at the beginning? 0. We don't have to do a Q calculation because there's none of this. It can't go left. There's nothing to go left. We only have left. It must go to the right. So what's going to happen? Some of this is going to convert to some of that until such a time that K is true. Now, in this problem, they're asking us, what is K? A lot of times we are given K, but this time we're going to figure it out. So what is K? Remember, it's products over reactants, the power of the number in front. I know the number in front is 1. I know the number in front is 2. So what I need is the numbers in here. This is going to be squared. This is going to be to the first. Well, let's examine this. I had 1.2 atmospheres to start, 0 of this to start. Some of this is going to convert. How much? Well, 2 will only get you 1. So this is going to lose something, and this is going to lose something, but this value is going to be twice as much in loss as this was in gain. Now then, I've tried this. I actually did test it out myself. You cannot call this x and 1/2 x. You have to use whole numbers because when you start multiplying fractions and so forth, they don't multiply the way whole numbers do. For instance, if you take half squared, you get 1/4, whereas really you should be taking 1 squared and get 1, right? Something like that. So we're going to use whole numbers. We're going to use 2. This is going to be twice the value lost as this is. So if we lost 10, we would get 5. X is 5. We lost 10 and we gained 5. So when this reaches equilibrium, we don't know what x is, but we will have lost 2x. And so this is what we would arrive at. We started with this, we lost this, this is where we arrive. We started here, we gained this, this is where we arrive. So the total pressure must be the pressure of this plus the pressure of this. And we know from the paragraph that they add up to 1. We can solve for x, and x is 0.2. Now, it's tempting to stop there and say, I found x, I must be done, but not in these problems. Be careful. Pay attention, because it's really tempting to do that, and everybody's done it. What are we getting? We're getting Kp. So what is this pressure at equilibrium? It's 1.2 minus double of 0.2. It's minus 0.4, so it's 0.8. And what's this? It is x. So this is 0.2. This really is x, and x is 0.2. So we will take the pressure of the 0.2 products, the power of the number in front, 1. We'll take this, remember this is 0.8, to the power of the number in front squared. And Kp turns out to be 0.31. Let's talk about manipulating the equilibrium constant, or changing it, because we might need to. And in fact, we're going to do an example down here in number 3 of why you might need to be changing the constant. We'll get to that in a minute. So here's our very common reaction of the production of ammonia. And the AP test loves this because it gets us a 1, a 2, and a 3 as the coefficients, and it's really simple otherwise. Plus, it's a classic manufacturing process. Now, Kc is 140 if they want to talk about it 800 Kelvin. Well, why so stupid hot? Well, that's probably the temperature it's commonly manufactured at, as a guess. Anyway, we're going to talk about it at 800 Kelvin, and I guess the Kc is 140 at that point. How did they get that? Products over reactants to the power of the number in front. H2 is to the third, and H3 is to the second. So if we had to do something like multiply this whole thing by 2, so if we had to do something like turn this all around, then the products became the reactants, and the reactants became the products. So now all this stuff is on top, and now this is on the bottom. And if you take your fraction and you flip it over, you get the inverse of the answer. So you don't get 140, you get 1 over 140. And just to show you, 1 divided by 140, 0.00714. Or inverse is to the -1 power. Go ahead and put it in your calculator. You really do get this. You get the same answer either way. What if you multiplied the whole original reaction by 3? Well, then all the K-math powers go up by 3. And what ends up happening is your answer is to the power of 3 compared to what it was. So it's not 140, it's 140 to the third. So if I doubled this, I would get 140 squared. If I multiplied by 4, all the way through, of course, I would get 140 to the 4th. So in this case, we're going to use both these at the same time. Look, we've reversed it. NH3 is on the left, and yet everything has also been multiplied by a half. So what that means is the reaction has done a flip because we reversed it left and right, and it's also everything's to the 1/2 power. So remember, we said if you reverse everything, you get to the -1 power, and if you multiply, then you get to that power. So we have Kc to the power of -1 times 1/2, which is -1/2. The exponent on this is -1/2, which is the inverse negative of the square root. So go ahead, grab a calculator, take the square root of 140 and then divide it under 1, and you get 0.085. As a matter of fact, it doesn't matter which way you do it. You can take 1 over 140 and take the square root of that answer, or you can take the square root of 140 and take it under 1. Either way, you get 0.085. So why would we need to be multiplying a reaction by 2 and 3.5 and stuff? Well, this does come up. This total reaction can be seen as the accumulation of these two partial reactions. And we know the K values at the temperature we want to discuss for these two partial reactions. But we're going to combine them so that they add up and cancel out to make this. And then we will find the K of the new one. I would look for something like in line 1 that doesn't occur anywhere else. And this is a pretty simple example because almost everything appears only once. But for instance, BAF2, does that appear anywhere else? No. Okay, that's going to make it nice. Now this needs to appear down here and in the right spot on the left or right of the arrow and in the right amount. So does it appear on the left of the arrow? It does. So let's not turn this equation around. It seems to be running the right way. And you can tell just from looking at one thing. We don't need to go and examine each of these things. This is on the correct side. Yes. Is it the correct amount? Yes, there is one of them. There is one of them. So this one, we're just going to leave. We're just check mark. That is done. We can extrapolate that if this is right, everything else is in the right position and in the right amounts. What about this one? HF, is that anywhere else up here? No. So that is a good choice. Is it on the correct side of the arrows? No, because it needs to be on the right side. So we are going to flip this reaction left and right. I'm going to do this so that it is on the right side. Is it the right amount? No, because it needs to be 2. So we are also going to multiply this by 2. And then you might notice that the F minuses don't appear down here. So what we just did had better cancel out the F minuses. So we had 2F minus on the right, and now this is 2F minus, and it's on the left. So in my new combined, when I take these two and squish them together, I have 2F minus left, 2F minus right, and now it is not really either a product or a reactant because it appears on both, so it wasn't produced, it didn't react. So it's just out of the reaction. It's not really part of the reaction overall. Because if you start with it and you end with it, then it didn't react. So it cancels out. So that's where it went. So we're going to, remember, double all these and turn them around. So 2H plus, this one cancels out with that one, and 2HF. Now, when you take these two and smash them together to make this, it turns out the KCs multiply as long as you remember to adjust for what you did. So we're going to take this one, unchanged, times this one, as long as you remember to take it to the power of -1 times 2. So we're going to take this value to the power of -2, which means it's really doing this. It's this over that because it needs to be in the denominator. Now that's what the negative does, but also squared while it's down there. So let's do one more practice with Q, although we have kind of done this. So here's my little reaction, and it needs to have the double arrow, doesn't it? KEQ is 5 because I said so because it's fake. At the moment, this exact moment, these are the values. Brackets means molarity, so we have molarities. And we said a gaseous or aqueous system. So we'll assume it's one or the other. It doesn't matter which. What is Q? Q is K math at this exact moment. So we'll take B to the first times C to the first over A squared, and we get 4. Well, when this is at equilibrium, that math should give us 5. So this is too small. What do we need? We need more numerator and less denominator. More numerator means more products. This system will shift to the right. The opposite would be true. If we get anything bigger than 5, we have too much numerator and not enough denominator, and it will shift to the left.